Hello, I'm here to talk with you today about radioactivity. My name is Alex Flood. I am a radiographer and healthcare educator. I currently teach two programs. I teach clinical medical assisting as well as a limited permit X-ray technician program in the state of California. This video is designed for my X-ray technician students so they can get a better understanding on what we mean when we say radiation and radioactivity. This should serve as a good introduction into the courses of radiation safety, as well as basic introduction to radiation physics. So what do we mean when we say the word radiation, right? So there's different categories of radiation. Radiation is simply energy in motion moving away from a source. That's all radiation means. We can think about waves in media. Water waves are a great example. In fact, they're kind of the shining example of what we mean when we say radiation that's not harmful radiation. We think of waves in water. Sound waves are an example of radiation. They're a compressional example of radiating waves, but they are waves of radiation. The other two categories, particulate radiation, are variations of protons and neutrons and electrons emitted at high speeds away from radioactive atoms. The third category, electromagnetic, these are double waves propagating in the magnetic and electric fields. These occur when electrons are in motion. An electron in motion has an electric field all the time, and when an electron moves, it generates a magnetic field. If you oscillate an electron back and forth, it oscillates the electric and magnetic field's location as it pertains to that electron, causing a wave in the medium of space. This medium, this is a wave that actually requires no medium, no ether to travel through. These include things like light, ultraviolet, infrared, microwaves, radio, TV, as well as X and gamma radiation. These are some definitions to get familiar with, some terms we'll be throwing around. If we talk about the Z number, we're talking about the atomic number, the number of protons in the nucleus of an element. You've all probably seen the periodic table of elements, giving you all of the elements that we know of. And the atomic number indicates how many protons there are. The atomic number tells us what element it is. You know, if you have an atomic number of 6, you are carbon. If you don't have an atomic number of 6, then you're not carbon. If you have an atomic number of 1, you're hydrogen, 2, you're helium. So the atomic number tells you what element you're working with. If the atomic number changes, if the Z number changes, the element has transmutated. Atomic mass is a little different. Atomic mass is just saying, what is the total mass of this element? Atomic mass includes all nucleons, everything in the nucleus, which is protons and neutrons. The neutron number is just N, capital N. You could know the neutron number if you knew the atomic mass and the atomic number. You could derive the neutron number no problem. Radioactivity is simply the spontaneous emission of radiation, either particles or photons from atoms. Usually we think of as unstable atoms. When an atom undergoes a radioactive event, we call it a decay event. An atomic nucleus with excess energy emitting a particle, either an alpha, beta, or gamma particle, to reach a more stable energy state. So this is transmutation of elements. There's two types that we should be familiar with. There is alpha radiation and beta radiation. Notice with alpha radiation, alpha emissions, an alpha emission is essentially equivalent to a helium nucleus. An unstable atom will emit 2 protons, 2 neutrons in a bundle called an alpha particle. Notice that this decreases the atomic number of the element. This causes the element to transmutate, to turn into a different element, because it loses 2 on its Z number, and its mass goes down by 4. Beta emissions, on the other hand, actually increase the Z number. Beta emissions occur when a neutron decays into a proton, an electron, and a neutrino. The neutrino is not mentioned here because it's not important for our purposes, but that's what a neutron is. A neutron is effectively a proton and an electron, a positive and a negative charge combined to equal a neutrally charged thing, and they can be unstable. When they do decay, the electron, being the lighter particle, is emitted from the atom, and you've effectively taken what was a neutron, turned it into a proton, so your Z number goes up by 1. You actually move up on the periodic table, and your atomic mass does not change. Your mass number does not change. Gamma emissions are an electromagnetic wave occurring when a unstable high-energy atomic nucleus returns or moves towards a more stable ground state. Gamma emissions don't change the atomic number, they don't change the atomic mass, they don't change the neutron number. Only some excess energy is emitted. The degree of harm caused by each depends on its mass and amount of electric charge. Alpha particles, being charged, having a charge of +2, will act on the orbital electrons that they pass by. Their large mass and their large charge makes them highly dangerous and highly ionizing. They can damage atoms. Beta particles can do this as well, not by attraction, but by repulsion. The beta particle can repel an orbital electron similar in at least concept to how you would take two magnets and stick the north poles facing each other and the magnets repel each other. Similar in concept to that. Natural radioactivity. So all of this was natural radioactivity. The extremely low penetration of alpha particles means that they deposit their energy in tissue into a more concentrated area. We refer to this as linear energy transfer. Alpha radiation transfers its energy, its kinetic energy, over a very small distance, which deposits the energy into a very small area. Alpha emitting particles aspirated to the lungs radiate this concentrated energy into local tissues in all directions. That is to say, all of the alpha particles emitted are absorbed by the tissues nearby. This is one reason why smoking is harmful. Penetration is inversely related to biologic harm. A non-penetrating radiation is actually the more harmful kind. You want radiation to penetrate through the body, and if you think about it, it makes sense. If radiation penetrates through the body, it's carrying that energy still that it did not deposit into the body. If radiation is not penetrating and it all absorbs within the body, then all of that energy was thereby absorbed within the tissue. More harmful in that case. This last table kind of sums up the things that I've been talking about. The types and characteristics of radiation. We have alpha, beta, gamma, and X. Alpha radiation is not penetrating, very harmful. It's very massive, about 8,000 times the mass of an electron, and it has a charge of +2. It comes from the nucleus of an atom. Beta radiation is not very penetrating, very harmful, has a mass of 1, the mass of an electron. Its charge is -1, and it comes from the nucleus. Gamma radiation is penetrating, more so than X-rays, less harmful than the first two types of particulate radiation. No mass, no charge. It's an electromagnetic wave, no mass, no charge. It comes from the nucleus, though. Effectively, the really major difference between gamma and X-rays, aside from their slight energy differences, are the source. Gamma rays come from the nucleus of an unstable atom, trying to regain stability, whereas X-rays, highly penetrating, less harmful, no mass, no charge, originate outside the nucleus. We say X-rays come from the oscillation of electrons, the movement of electrons. Thank you. I hope you enjoyed this small video on radioactivity. Please check back later for more. Thank you.